There is a clock. You can't see it. You can't hear it. No instrument ever built by human hands can detect its ticking. And yet, it is counting down. Right now, in this precise moment as you're watching this video, as the world outside your window hums with traffic and light, and the ordinary unremarkable details of another day, the universe is closer to its death than it has ever been before. That sentence sounds dramatic. It's supposed to. But here's the part that will genuinely change how you think about your place in the cosmos. When you zoom out far enough, when you stop measuring time in years or centuries or even millions of years, and instead start measuring it on the timescale the universe actually operates on, the timescale of trillions of years, of numbers so vast they break our intuition like a twig underfoot, you realize something deeply strange and humbling. You're not living in the middle of the universe's story. You're not even living near the beginning of the end. You're living in a razor-thin sliver of cosmic time, a period so anomalously brief, so extraordinarily lucky, so fundamentally temporary that future civilizations, if they could ever exist to look back, might well describe this entire era of stars and galaxies and light and life as a single fleeting heartbeat in the otherwise cold, dark, near-infinite silence that follows. We are living in the last seconds of the universe, not in the sense that the end is coming tomorrow, not in the sense that you need to look up from your phone and say your goodbyes. The universe has many, many long chapters ahead of it. But those chapters are not chapters filled with stars and light and the warm energy that makes existence the way we know it possible. They are chapters of darkness, of cold, of matter, dissolving back into its most basic components, of silence so complete it would make the emptiness between galaxies feel positively cozy. The fire we live inside, the brilliant, luminous, stelliferous era of star formation and planetary systems, and the kind of energy gradients life depends on, is already burning down. The peak of star formation in the universe happened roughly 10 to 11 billion years ago, when galaxies were bursting with the births of thousands of new stars every single year. Today, the star formation rate across the entire observable universe has declined by approximately 97% from that peak. We are living in the slow twilight of the age of stars, not its morning. So let's start by figuring out exactly where we are. The universe is 13.8 billion years old. 13.8 billion years. That number is so large that our brains genuinely struggle to do anything useful with it. So let's try a different approach. Imagine compressing the entire history of the universe, from the Big Bang to this very second, into a single calendar year. The Big Bang happens at midnight on January 1st. Our sun doesn't form until September 2nd. Earth forms 4 days later, on September 6th. The first single-celled life appears somewhere around September 21st. The first complex multicellular life only shows up around December 5th. The dinosaurs appear on December 25th, Christmas Day, and they go extinct 4 days later, on December 29th, when a rock 6 miles wide punches through the atmosphere and changes everything. Modern humans, Homo sapiens, the species capable of making YouTube videos about the death of the universe, appear at roughly 11:52 in the evening on December 31st. The entirety of recorded human civilization, every empire, every scientific revolution, every war, every work of art, every single thing written down and remembered, all of that fits into the last 15 seconds of December 31st. Now, knowing all of that, knowing how minuscule we are on the scale of the universe's past, here is the part that will genuinely disturb you, or thrill you, or both at the same time. On the scale of what comes next, of what the universe will eventually become, our compressed one-year timeline is not even the whole calendar. It is less than a single breath of January 1st. It is the first fraction of the first fraction of the first second after the Big Bang equivalent. The universe's story is almost entirely in the future, and it is not a story about light and warmth and stars. It is a story about cold and darkness, and the slow, patient dissolution of everything that exists. Let's find out what happens. Before we start traveling through the future, we need a map. Without a map, the numbers become so enormous they stop meaning anything. They stop feeling real. We need a framework that lets us navigate time on a scale that leaves billions of years behind, as if they were nothing but stepping stones across a stream. The map we're going to use was largely created by two astrophysicists named Fred Adams and Gregory Laughlin, who in 1999 published a book called The 5 Ages of the Universe. Adams was based at the University of Michigan and Laughlin at the University of California, Santa Cruz. Together they constructed what is, to this day, one of the most remarkable intellectual frameworks ever built. A complete chronology of the cosmos from its first moments to its ultimate fate, organized into 5 great eras. Think of these eras as chapters in a book so long that writing it would itself take longer than the universe has existed so far. Understanding these 5 chapters is the essential foundation for everything we're about to explore. Adams and Laughlin used a clever system to handle the mind-bending timescales involved. Rather than writing out numbers with dozens of zeros, they used something called cosmological decades. A cosmological decade is simply a power of 10. Cosmological decade 5 means 10 to the power of 5 years, which is 100,000 years. Cosmological decade 10 means 10 to the power of 10 years, which is 10 billion years, roughly the current age of the universe. Cosmological decade 20 means 10 to the power of 20 years, 100 million trillion years. The system lets you navigate an unimaginably vast timeline using a simple, manageable scale, like measuring an ocean voyage in increments of latitude rather than in individual strokes of a paddle. The first era is the primordial era, and it covers cosmological decades -50 all the way to +6. In practical terms, this is the first million years after the Big Bang. During this era, the universe is an unimaginably hot, dense, rapidly expanding sea of energy and exotic particles. It cools as it expands. Protons and neutrons form in the first fractions of a second. Nuclei form in the first few minutes. The Big Bang nucleosynthesis that creates hydrogen, helium, and trace amounts of lithium. Hundreds of thousands of years later, the universe cools enough for electrons to bind to nuclei and form the first atoms. When that happens, the universe becomes transparent for the first time. Light travels freely. That ancient light is what we still detect today as the cosmic microwave background radiation. A faint afterglow filling the entire sky, a fossil image of the universe in its infancy. The primordial era is the origin story, the setup. The universe assembles its basic ingredients. Then comes the era we live in, the stelliferous era. The word stelliferous means filled with stars. This is cosmological decade 6 through 14, meaning it covers the period from roughly 1 million years after the Big Bang to approximately 100 trillion years after the Big Bang. It is the age of galaxies and stars and planets and chemical complexity and biology and everything that anyone has ever cared about in the entire history of anything. The light we see from the sky tonight is stelliferous era light. The sun warming the surface of the Earth is stelliferous era energy. Every civilization that has ever existed, including ours, has existed entirely within the stelliferous era. But here is what you need to sit with: the stelliferous era, despite spanning 100 trillion years in total, will ultimately rank as one of the shortest eras in the universe's history. It will end, and what comes after it is not life as we know it, continuing under new conditions. What comes after it is a series of increasingly dark, increasingly cold, increasingly desolate epochs that together dwarf the stelliferous era the way an ocean dwarfs a raindrop. After the stelliferous era ends, after the last star burns out, we enter the degenerate era. This is cosmological decades 15 through 39, meaning it spans from 100 trillion years after the Big Bang to roughly 10 to the power of 37 years after the Big Bang. To put that number in perspective, 10 to the 37 is 100 quadrillion. We don't have a word in everyday English for a number that large. The degenerate era is a universe of stellar corpses, white dwarfs, cooling toward absolute zero, neutron stars spinning silently in the dark, brown dwarfs that never quite made it to starhood drifting alone through the expanding void. It is a universe of matter without energy, a universe of objects without light. But even that is not the end. After the degenerate era, matter itself begins to come apart. We enter the black hole era, cosmological decades 40 through 100. This is the age when the only organized structures left in the universe are black holes, vast gravitational pits formed from the collapse of entire galaxies, containing the mass of billions of stars, slowly bleeding away into radiation through a quantum mechanical process that Stephen Hawking described in 1974. These black holes are the last strongholds of organised matter in the universe. They are the final embers in a hearth gone cold. And then even those are gone. The dark era begins around cosmological decade 100, and it goes on, well, there is no word for how long. It is a universe of photons slowly redshifting toward infinite wavelength, of electrons and positrons drifting alone through a void so vast that the average distance between particles is larger than the entire observable universe today. It is a universe in which nothing ever happens, because there is no thermodynamic gradient left for anything to happen with. It is a universe of maximum entropy, complete thermodynamic equilibrium, heat death. That is the map. 5 eras: primordial, stelliferous, degenerate, black hole, dark. We live in the second one, and the second one, relative to everything that follows, is already almost over. Now let's walk through each chapter in detail, starting with understanding exactly where we are and why the era we live in is already winding down. The universe started making stars approximately 400 million years after the Big Bang. The very first stars were nothing like the stars we know today. They were enormous, ferociously energetic objects, hundreds of times more massive than our Sun, burning through their fuel at a rate so savage that their entire lives lasted only a few million years. A flicker in cosmic terms. These first stars, which astronomers call population 3 stars, lived and died so quickly that none of them survive today. We've never directly observed one. They burned so hot that they were largely featureless, composed almost entirely of hydrogen and helium, containing none of the heavier elements, carbon, oxygen, iron, that later generations of stars would forge and scatter across the cosmos. Those first stars died in spectacular supernova explosions that seeded the universe with the first generation of heavier elements. Their debris became the raw material for the next generation of stars, and those stars in turn lived, died, and enriched the gas clouds around them further. This process repeated over billions of years, each generation of stars building on the chemical legacy of the last, until eventually you had stars like our Sun and, around those stars, rocky planets built from the stardust of a dozen previous generations. The carbon in your body was made in the cores of stars that exploded before our Sun was born. The iron in your blood was forged in a supernova. You're not separate from the stelliferous era. You are one of its products. The peak of this era of star formation, the moment when the universe was most vigorously and prolifically making new stars, is called cosmic noon. Cosmic noon happened roughly 10 to 11 billion years ago, when the universe was only about 3 to 4 billion years old. During cosmic noon, galaxies like the Milky Way were forming thousands of new stars every single year. The cosmos was lit up like a city seen from an airplane at night, dense concentrations of light packed into the tendrils of the cosmic web connected by great filaments of gas and dark matter. It was the brightest, most energetically active period in the history of the universe. Everything since then has been a slow, inexorable dimming. Since cosmic noon, the rate at which the universe forms new stars has been declining continuously. Today, according to comprehensive surveys using instruments including the Hubble Space Telescope, the James Webb Space Telescope, and the Atacama Large Millimeter Array, the star formation rate across the observable universe is only about 3% of what it was at its peak. The universe still makes new stars, but it does so hesitantly, slowly, in galaxies that are running low on the cold molecular gas needed for star formation to occur. The reason for this decline is partly the depletion of usable hydrogen gas. As galaxies age, their reservoirs of fresh star-forming material get used up, converted into stars and stellar remnants that can no longer feed the cycle. Dark energy also plays a role, driving galaxies apart so that the galaxy mergers that once triggered huge bursts of star formation become less common. The universe has moved from its morning to its late afternoon. The light is still there, but it's going golden, and the long shadows are coming. Now here is something that should give you pause. We said the stelliferous era spans from roughly 1 million years to 100 trillion years after the Big Bang. That's a span of essentially 100 trillion years, and yet we find ourselves here at 13.8 billion years. That means we are at approximately 0.0138% of the way through the stelliferous era. We haven't even gotten to the era's midpoint yet, let alone anywhere near its end. So in that sense, we are genuinely early in the age of stars. But here's the crucial wrinkle. the vast majority of the stelliferous era's remaining years will not be like the universe we live in now. The Sun is a medium-mass star. Medium-mass stars like the Sun burn bright and die relatively quickly. The Sun has been shining for about 4.6 billion years and has roughly another 5 billion years of hydrogen-burning life left in it. After that, it will expand into a red giant, swallowing Mercury and Venus and quite possibly Earth, before shedding its outer layers and leaving behind a white dwarf, a dense, cooling ball of carbon and oxygen about the size of Earth, slowly fading over billions of years. Massive stars, the ones many times heavier than the Sun, live even faster and die even more violently. A star 20 times the mass of the Sun might last only 8 million years before exploding as a supernova and collapsing into a neutron star or black hole. These massive stars, the ones that produce the most dramatic light and energy, and that enrich the cosmos most effectively with heavy elements, are already essentially gone in the Milky Way. We are in a period of late-stage stellar evolution. What remains? What will dominate the stelliferous era for the overwhelming majority of its remaining 100 trillion-year span are red dwarfs. Red dwarfs are small, dim, slow-burning stars with masses ranging from about 8% to about 60% of the Sun's mass. They are so cool that they glow red rather than white or yellow. Many are so dim that even in a dark sky they would be invisible to the naked eye. You have probably never thought about red dwarfs, and yet they make up approximately 70 to 75% of all the stars in the Milky Way. In the entire observable universe, red dwarfs outnumber every other type of star combined, and they live for an unimaginably long time. A red dwarf with 10% of the Sun's mass has an estimated main sequence lifetime of roughly 10 trillion years. That is approximately 700 times the current age of the universe. The smallest red dwarfs, those teetering on the very edge of the minimum mass needed to sustain nuclear fusion, can burn for close to 12 trillion years, more than 800 times the age of the universe as it currently stands, and not a single one of these stars has yet reached its later stages of development. Every red dwarf that has ever formed is still on the main sequence. They are all still in the hydrogen-burning phase. They have barely begun. So the stelliferous era's long twilight years will be largely a universe of red dwarfs. Dim, small, barely visible stars scattered through the expanding void, burning their hydrogen with extraordinary patience, their worlds bathed in a faint reddish glow that would make the night sky look like it's permanently lit by embers. There will likely be planets around many of these stars. Some of those planets might have conditions compatible with life, but the universe will be quieter, emptier, colder, and darker than the universe we know, because all the massive, brilliant, short-lived stars that currently illuminate the cosmos will be long gone. Gradually, over tens of trillions of years, even the red dwarfs run out of hydrogen. One by one, they exhaust their fuel. Unlike sun-like stars, red dwarfs don't swell into red giants. They don't have enough mass for that. Instead, they slowly contract and fade, becoming helium-white dwarfs, cooling balls of degenerate matter no bigger than a planet, glowing faintly from residual heat, before gradually going dark over billions more years. The last red dwarf star in the universe is expected to burn out somewhere around 100 trillion years from now. When that last star goes dark, the stelliferous era ends. The lights go out. Everything we have ever known, everything biology has ever produced, everything human civilization has ever aspired to, all of it is confined to a universe in which at least one star is still burning. Once that last star extinguishes, we cross a threshold from which there is no return. We leave the age of light. We enter the dark. Before we move past the era of stars entirely, we should zoom in and understand what the stelliferous era's twilight years look like in our own cosmic neighbourhood. Because the Milky Way is not going to float serenely through all of this unchanged. Our galaxy has its own story unfolding on cosmological timescales, and that story involves one of the most dramatic events in all of astronomy, a collision with our nearest large neighbour, the Andromeda Galaxy, known also by its catalogue designation M31, is the most distant thing you can see with the unaided eye. On a dark night, it appears as a faint smudge of light about 2.5 million light-years away, in the direction of the constellation Andromeda. Most galaxies in the observable universe are moving away from us, carried by the expansion of space. Andromeda is different. It is approaching us. The Andromeda Galaxy is hurtling toward the Milky Way at roughly 250,000 miles per hour, about 400,000 kilometers per hour, and the two galaxies are on a collision course. Astronomers have been studying this impending merger for decades, and the current best estimates suggest that the first close encounter between the two galaxies will happen in roughly 4 to 5 billion years. A 2012 study using the Hubble Space Telescope, which tracked the motions of individual stars in Andromeda over a 7-year baseline, concluded that a direct collision was essentially inevitable. The two galaxies will pass through each other, then swing back, then merge, over a process that will take several billion years to complete. The resulting elliptical galaxy, a rounded blob of stars rather than the elegant spiral structures we know today, has been nicknamed Milkomeda by astronomers, a mashup of the two parent galaxies' names. It's worth noting that very recent simulations from 2025 have introduced some uncertainty into this prediction, with some models suggesting roughly a 50-50 chance of the collision occurring within the next 10 billion years. But even in scenarios where the two galaxies avoid immediate collision, they remain gravitationally bound and are expected to eventually merge. Now, a word of comfort before this sounds too alarming. The collision of the Milky Way and Andromeda will not be dangerous in the way that collisions in everyday life are dangerous. The average distance between stars, even in the dense centre of a galaxy, is trillions of miles. Stars are not packed tightly like marbles in a jar. They are separated by vast, empty stretches of space. When the two galaxies pass through each other, the odds of any individual star colliding with another are extraordinarily low. What will change is the structure. Tidal forces will stretch and distort both galaxies. Long streamers of stars will be flung out into intergalactic space. Gas clouds will collide and compress and trigger new bursts of star formation in the aftermath of the merger. If you were alive on a planet somewhere in either galaxy during the collision phase, you would see the sky gradually transformed. Andromeda growing from a faint smudge to a huge, spectacular presence, filling a significant portion of the night sky, and eventually the two galactic structures merging into a single, dramatically different shape. But the significance of this collision, in the context of the universe's long-term story, is not just aesthetic. It is one of the last major galaxy mergers that our local cosmic neighborhood will experience. Because dark energy is accelerating the expansion of space, the clusters and superclusters of galaxies farther away from us are already receding faster than the speed of light, not because they're moving through space at that speed, but because the space between us and them is itself expanding. Over billions of years, those distant galaxies will cross what's called the cosmological event horizon, the boundary beyond which not even light can ever reach us. They will disappear from our observable universe forever, not because they cease to exist, but because the expanding space between us and them becomes an uncrossable gulf. The local group, the collection of galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and a few dozen smaller dwarf galaxies, is gravitationally bound together. These galaxies are not being pulled apart by dark energy because the gravitational attraction between them is strong enough to overcome the expansion on that scale. They will stick together, eventually merging into a single massive elliptical galaxy. But beyond the local group, the rest of the universe is already leaving us behind. In the far future, astronomers living in whatever civilization exists around those last dim red dwarfs will look out at a sky nearly empty of galaxies, because everything beyond the local group will have receded over the cosmological horizon billions of years earlier. That is a profound isolation, and it matters for what comes next, because the raw material for new stars comes from fresh gas being brought in by galaxy mergers. Once the local group finishes its long consolidation into a single object, once no more fresh gas is available, and once the existing reserves of hydrogen have been consumed by the last generation of red dwarfs, there will be no more stars. Not ever again. The stelliferous era ends with the extinguishing of the last red dwarf, somewhere around 100 trillion years from now. What follows is the degenerate era, and it is profoundly different from anything that came before it. The universe does not simply go dark all at once. It goes dark by degrees, and each degree is marked by a different class of stellar remnant slowly cooling, slowly fading, slowly falling toward equilibrium with the ever-expanding, ever-cooling void around it. When stars die, They don't vanish. They leave things behind. The most common kind of remnant is the white dwarf. When a star like our Sun reaches the end of its hydrogen-burning phase, it swells into a red giant, possibly expanding to hundreds of times its original size and engulfing the inner planets. Then it sheds its outer layers in a spectacular cloud of ionized gas called a planetary nebula, exposing the hot, dense core beneath. That core, composed mainly of carbon and oxygen, incredibly dense, roughly the size of Earth despite containing perhaps half the original star's mass, supported against further collapse by a quantum mechanical effect called electron degeneracy pressure, is the white dwarf. Initially, a newly formed white dwarf glows white hot. Over billions of years it cools, becoming yellow, then orange, then red, then infrared, then invisible. In theory, after an unimaginably long time, a white dwarf cools to the temperature of its surroundings and becomes what physicists call a black dwarf, a cold, dark ball of crystallized carbon and oxygen floating silently through space. There is one important detail about black dwarfs. They do not yet exist. The universe is not old enough for even the oldest white dwarfs to have cooled to that state. The cooling process takes trillions of years, and the universe has only been around for 13.8 billion years. So the degenerate era will be populated, at least initially, by white dwarfs still slowly radiating the last of their stored heat, along with neutron stars, the dense remnants of massive stellar explosions, and brown dwarfs, objects that formed like stars but never accumulated enough mass to ignite nuclear fusion, leaving them as cold, dark, mostly inert objects drifting through the void. The dynamics of the degenerate era are driven by gravity, operating over enormously long timescales. Galaxies, or rather, the consolidated remnant of everything the local group will eventually merge into, will undergo what physicists call dynamical relaxation. This is a process where gravitational interactions between the stellar remnants within a galaxy gradually redistribute energy and angular momentum over time. The result is that some stellar remnants, the lighter ones, receive enough energy from close gravitational encounters with heavier objects to reach escape velocity and get flung out of the galaxy entirely. Astronomers call these ejected objects evaporating from the galaxy. Meanwhile, heavier objects lose energy in those same interactions and spiral inward, collecting at the galaxy's center. Over timescales of about 10 to the power of 19 years, tens of billions of times longer than the current age of the universe, entire galaxies of stellar remnants will reorganize themselves this way, with a dense central concentration of mass and a thin halo of escaped objects drifting alone through intergalactic space. The central concentrations will likely be swallowed by the supermassive black holes that have been sitting at the hearts of galaxies since early in the Stelliferous era. Our own Milky Way has a supermassive black hole called Sagittarius A star, which currently has a mass of about 4 million times that of the Sun. During the degenerate era, as stellar remnants spiral in and are consumed, these black holes will grow, though by this point there won't be much in falling material left except cold, dark objects moving slowly under gravity. But here's where the degenerate era gets genuinely weird, in a way that reaches down into the nature of matter itself. If a theoretical prediction first proposed by certain extensions of particle physics, called grand unified theories, is correct, protons are not actually stable. The proton, the positively charged particle at the heart of every atomic nucleus, the building block of all visible matter, may eventually decay into lighter particles. The predicted half-life of a proton varies depending on the specific model, but rough estimates place it at around 10 to the power of 34 to 10 to the power of 37 years or so. This has not been confirmed experimentally. Experiments like the Super Kamiokande detector in Japan, a vast tank of 50,000 tons of ultra-pure water buried deep underground and surrounded by thousands of light detectors, have been watching for signs of proton decay for years and have so far detected nothing. This has allowed physicists to constrain the proton's half-life to be at least 10 to the power of 34 years, but it has not ruled out the possibility that protons do eventually decay. If proton decay does occur, the consequences for the degenerate era are profound. Remember that every solid object in the universe, every white dwarf, every black dwarf, every neutron star, every planet, every molecule, every atom of anything made from protons and neutrons, is, in the presence of proton decay, only temporary. Given enough time, the protons making up those objects will spontaneously transform into lighter particles, positrons, pions, electrons, gamma rays. The object itself simply dissolves, not through any external force, not through collision or impact, but through the quiet statistical certainty that every proton will eventually fail to remain a proton. The timescale over which all the protons in a single stellar remnant would decay is around 10 to the power of 37 to 10 to the power of 39 years, numbers so vast they dwarf the entire previous history of everything that has existed since the Big Bang by a factor of trillions. But in the universe's infinite patience, that time arrives, and when it does, the last solid object, the last white dwarf, the last frozen black dwarf, the last rocky planet orbiting a cold stellar corpse, dissolves into a thin mist of fundamental particles. If proton decay does not occur, if protons turn out to be truly stable, then the degenerate era stretches even further, with matter persisting longer in various configurations. But even proton stability cannot prevent the eventual end of organized matter, because the black holes will still be there, and the black holes have their own mechanism of dissolution. While all of this is unfolding on timescales of trillions and quadrillions of years, dark energy continues doing exactly what it has been doing since roughly 6 billion years after the Big Bang, pushing everything apart. And as the universe ages, this relentless cosmic expansion becomes increasingly dominant and increasingly lonely. Dark energy is one of the most remarkable things we have ever discovered, and we barely understand it. It makes up roughly 68 to 70% of the total energy content of the observable universe. It is not like ordinary energy in any obvious sense. It does not clump. It does not interact with matter in any directly detectable way. It does not dilute as the universe expands. In fact, by most models, as the universe grows larger and the total volume of space increases, the total amount of dark energy increases proportionally with it, maintaining a constant energy density even as space stretches. This is why its expansion effect doesn't fade over time the way the effects of ordinary matter and radiation do. The result is that the universe's expansion is not just continuing but accelerating. The farther a galaxy is from us, the faster it is receding. Beyond a certain distance, the cosmological event horizon, galaxies are already receding faster than the speed of light, not because they are physically moving through space at superluminal speeds, but because the space itself between us and them is expanding fast enough to outpace any signal. Those galaxies are already causally disconnected from us, gone forever. Their light will never reach us again, and over the long future of the universe this isolation deepens. Today, the observable universe contains roughly 2 trillion galaxies, but the number of galaxies within our causal reach, the number we could, in principle, ever interact with or receive light from, has been declining since dark energy began to dominate, about 6 billion years ago, and it will continue to decline. In the far future, the only galaxies visible from any point in the universe will be those in the immediate gravitational neighborhood, the local groups and clusters that are bound together against the expansion. Everything else will have receded beyond the horizon. This is not just a practical limitation. It is a deep structural change in what the universe is. The universe is not merely growing, it is fragmenting into isolated islands. Each gravitationally bound group of galaxies becomes its own universe in a practical sense, a collection of matter that can see only itself and the void around it, with no connection to the rest of the cosmos. From the perspective of an observer in one of those islands, the universe will appear to consist only of their local group. All other galaxies will have vanished over the horizon billions of years earlier, leaving the sky stripped of everything but nearby stars and eventually nearby stellar remnants. There's another consequence of this accelerating expansion that is easy to overlook but deeply important. The cosmic microwave background, that faint relic radiation filling the universe from the era when it became transparent, will continue to cool and redshift as the universe expands. Currently, the CMB has a temperature of about 2.7 Kelvin, only 2.7 degrees above absolute zero. As the universe expands, the CMB cools further. Eventually, far in the future, the CMB radiation will have been stretched to such long wavelengths and cooled to such low energies that it will be essentially undetectable by any conceivable instrument. The universe will lose even its faint warm glow, and dark energy raises another, even stranger possibility, though one that current observations do not favour. If dark energy is not a constant but instead grows stronger over time, if its equation of state is what physicists call phantom dark energy, with what's technically described as a value for the parameter due that is less than -1, then the expansion doesn't just accelerate gradually, it accelerates exponentially, with the expansion rate growing without limit. Under those conditions, the expansion could eventually overpower not just the gravity holding galaxies together, but the electromagnetic forces holding molecules together, the nuclear forces holding atomic nuclei together, and ultimately even the quantum fields that maintain the stability of protons and electrons. Everything would be literally ripped apart as space expands faster and faster between every pair of particles. This scenario is called the Big Rip. Current best measurements suggest we are not in a Big Rip universe. The data from supernova surveys, from the cosmic microwave background, and from the large-scale structure of the universe all point to dark energy behaving like a cosmological constant, a fixed amount of energy per unit volume, not growing with time. But we don't fully understand dark energy. The honest answer, from the physics community, is that we do not know what dark energy fundamentally is. It could be the cosmological constant first, introduced by Einstein, and then abandoned. It could be a scalar field called quintessence with its own dynamics. It could be something entirely outside our current theoretical framework. And without understanding what it is, we cannot be completely certain what it will do in the far future. What we're confident about is the baseline trajectory. If dark energy remains constant, the universe expands forever, cooling as it goes, with organized structures, galaxies, stars, eventually even stellar remnants, becoming increasingly isolated in an increasingly vast, cold, dark void. The temperature of the universe asymptotically approaches something close to absolute zero. And the second law of thermodynamics, the principle that entropy in any closed system will always increase or stay the same, drives everything relentlessly toward a state of maximum disorder, minimum usable energy, and complete thermodynamic equilibrium. That is the end game. But before we get there is one more class of objects that needs to be dealt with: the black holes. Don't understand. After the degenerate era ends, after the stellar remnants have either decayed through proton dissolution or been consumed by the central black holes of galaxy clusters, the universe enters what Adams and Laughlin call the black hole era. This spans from approximately cosmological decade 40 to cosmological decade 100, meaning from roughly 10 to the 40 years to 10 to the 100 years after the Big Bang, numbers that are not just large but cosmically, offensively, almost self-parodically large. By this point, the only surviving organized structures in the entire universe are black holes. Everything else, all the stars that ever shone, all the planets that ever formed, all the matter that ever coalesced into anything recognizable, has either been swallowed by black holes, dissolved through proton decay, or scattered as individual particles so far apart that meaningful interactions between them are essentially impossible. The universe is cold, dark, almost entirely empty, and yet not quite finished. Black holes are strange objects, and they are stranger still when you bring quantum mechanics into the picture. In classical general relativity, Einstein's theory of gravity, a black hole is an object from which nothing can escape, including light. Once matter or energy falls within the event horizon, it is gone from the universe's accounting forever. The black hole simply grows as it consumes. In this classical picture, black holes are eternal and only ever get larger. But in 1974, Stephen Hawking showed that this cannot be quite right. When you apply the principles of quantum mechanics to the space immediately outside a black hole's event horizon, something extraordinary happens. Empty space is not truly empty at the quantum level. It seethes with virtual particle pairs spontaneously appearing and annihilating each other on timescales too short for energy conservation to notice. Normally these virtual particles appear and immediately annihilate. But right at the edge of a black hole's event horizon, it becomes possible for one particle of a virtual pair to fall into the black hole while its partner escapes into the wider universe. The escaping particle is real radiation, and since that radiation carries energy away from the black hole, and energy and mass are equivalent, the black hole slowly loses mass. This process is called Hawking radiation, and it is so extraordinarily slow that for any black hole that exists in the current universe, It is completely swamped by the tiny amounts of matter those black holes still occasionally absorb. The black holes we can observe today are not evaporating. They are still, in net terms, growing or at best staying the same size. But in the far future, once the universe is empty enough that nothing falls into them anymore, they will begin to evaporate, and eventually, after enough time, they will evaporate entirely. How long does this take? For a stellar mass black hole, one formed from the collapse of a single large star, with a mass perhaps 10 to 20 times that of the Sun, the evaporation time through Hawking radiation is approximately 10 to the power of 67 years. That number dwarfs the current age of the universe by a factor of more than 10 to the 57. Even in our compressed cosmic timeline, this is an unimaginable span of time after the present. For a supermassive black hole, the kind sitting at the centre of a large galaxy, with a mass billions of times that of the Sun, the evaporation time is even longer. The supermassive black hole at the centre of the Milky Way, Sagittarius A star, with its mass of about 4 million solar masses, would take roughly 10 to the power of 87 years to evaporate. The supermassive black hole at the centre of the galaxy M87, which has a mass of approximately 6.5 billion solar masses and was famously the first black hole ever directly imaged by the Event Horizon Telescope in 2019, would take something in the neighbourhood of 10 to the power of 100 years to evaporate completely. That number, 10 to the 100, has a name that you might have heard before, a googol, one followed by 100 zeros. Even by the already astonishing standards of numbers we've been throwing around tonight, a googol is breathtaking. If you tried to write out a googol in standard notation, the number itself would contain more digits than there are atoms in the observable universe, and that is approximately how long the very largest black holes will persist. As a black hole evaporates, it also radiates. In its final stages, Hawking radiation becomes intense. A black hole near the end of its life, having shrunk from billions of solar masses to something incredibly tiny, heats up dramatically and releases a final burst of energy before vanishing. Physicists sometimes describe the final instant of a black hole's evaporation as a flash of radiation, the last cry of the most persistent object the universe ever produced. What's left after that flash is essentially nothing, a brief pulse of gamma rays expanding outward, and then silence. In the black hole era, those flashes mark moments of loss. One by one, the last organized objects in the universe cease to exist. A flash here, a stellar mass black hole gone. A flash somewhere else, billions of years later, a galactic mass black hole gone. The flashes become less and less frequent. The intervals between them stretch to spans that mock the word time, and then eventually the last flash, the last organized object in the universe, gone. After that comes the dark era. The dark era begins when the last black hole evaporates. It is, by definition, the longest era in the universe's history, because it has no predictable endpoint. It stretches from cosmological decade 100 outward, past 10 to the 100 years, past 10 to the 1000 years, past any number you care to name, and does not end in any conventional sense. The universe does not stop existing. It continues. It simply contains nothing of interest. By the time the dark era arrives, the universe is a thin, almost incomprehensibly dilute gas of photons, neutrinos, electrons, and positrons. Particles so far apart from each other that the average distance between any two of them is not just larger than the observable universe as it is today, but many orders of magnitude larger than any scale we have ever used in physics. The photons that exist are the last remnants of Hawking radiation, stretched to enormous wavelengths by the continuing expansion of space. They carry so little energy that they make today's cosmic microwave background look like a roaring furnace by comparison. The temperature of the universe in the dark era is not zero. Absolute zero is a theoretical limit that can be approached but never quite reached. Instead, the temperature is unimaginably close to zero, separated from it only by the faint warmth of the expanding universe's de Sitter horizon temperature, a value so small it would require dozens of decimal places to express. For all practical purposes, nothing can happen in the dark era. There are no energy gradients large enough to drive any chemical process. There is no usable free energy anywhere in the universe. The second law of thermodynamics has completed its work. entropy has reached its maximum. This is what physicists call heat death, or the big freeze. It is not a dramatic explosion or a violent collapse. It is an asymptotic approach to total equilibrium, a universe that becomes progressively more homogeneous, more uniform, more static, until the very concept of change loses meaning. Time technically still passes in the dark era, but nothing marks its passage. No clocks tick, no stars shine, no reactions occur. The universe persists in a state of perfect frozen equilibrium, expanding forever, cooling, toward a temperature that can never quite reach absolute zero, in a silence so complete that the word silence fails to capture it, because silence implies the absence of something that was once there, and in the dark era there is nothing that was ever anywhere else to be absent from. There is one last thought experiment worth sitting with, even though it's deeply speculative. In the late 1800s, physicist Ludwig Boltzmann, working on statistical mechanics and the nature of entropy, proposed that in a universe of infinite age and infinite volume, quantum and thermal fluctuations would, given enough time, spontaneously produce structures of any given configuration, including theoretically a complete human brain, fully formed, with all its memories and consciousness intact, appearing for a brief moment from the random statistical noise of a near vacuum. This hypothetical object is called a Boltzmann brain. The math behind Boltzmann brains is uncomfortable. Given truly infinite time, a random fluctuation that produces a conscious mind is not just possible, but statistically certain to occur, and to occur an infinite number of times. This creates a paradox. If the universe is old enough and large enough for Boltzmann brains to be overwhelmingly common, then any randomly selected conscious observer should statistically be a Boltzmann brain rather than a normal human who evolved through natural processes. We are not Boltzmann brains. Our memories are consistent. Our environment is coherent. The laws of physics work the way they should work. This is actually evidence, in a roundabout way, that the universe either does not last long enough in the right configuration for Boltzmann brains to dominate, or that our models of the universe's far future are incomplete in ways that prevent the problem from arising. Most modern cosmologists think the Boltzmann brain problem is avoided by the eventual decay of the vacuum itself. The idea that the quantum field configuration of the universe, including dark energy, is not truly in its absolute lowest energy state, but in a metastable false vacuum that will eventually probabilistically decay to a lower energy true vacuum through a process of quantum tunneling. When a false vacuum decays, it happens through bubble nucleation. A tiny region of true vacuum spontaneously appears and then expands at the speed of light, changing the physical constants of the universe as it goes. Within that bubble, atoms cannot form, chemistry cannot happen, and nothing like life or Boltzmann brains can exist. If vacuum decay happens before the dark era reaches the stage where Boltzmann brains would be likely, the problem is avoided. Whether vacuum decay will happen, and when, is not currently known. It depends on the precise energy landscape of the Higgs field, which physicists are still working to determine from experimental data. Some calculations suggest that our current vacuum might be metastable, with a decay time far longer than the current age of the universe. Others suggest greater stability. It is genuinely one of the open frontiers of theoretical physics. But even setting aside the exotic possibility of vacuum decay, the dark era's endpoint is already strange and complete enough. The universe reaches maximum entropy. All useful energy is gone. All organized structure has dissolved. The cosmos exists in a state of permanent, perfect, featureless equilibrium. The laws of thermodynamics have been satisfied. The universe, for all practical purposes, is finished, and this is the universe's default future, given our current best understanding of physics. Not a dramatic big crunch, not a big rip that tears atoms apart. Those scenarios require dark energy to behave differently than our best measurements currently indicate. The most likely fate, the one most consistent with what we actually observe, is the quiet, patient, slow grinding toward equilibrium. The big freeze, heat death. The universe going not with a bang but with the quietest possible whisper, and then not even that. The far future is almost too abstract to hold in the mind. 10 to the 100 years is not something any human being will ever meaningfully experience. But here's the thing. The universe is near future. The part that is relevant on timescales of billions of years rather than trillions of trillions. is full of events that are enormous, concrete, and coming with the same certainty as the sunrise. The Sun has roughly 5 billion years of hydrogen-burning life remaining. That is a long time. It is more than the current age of the Earth. But in cosmic terms, the Sun is middle-aged. Already, over its 4.6 billion-year life, the Sun has become about 30% more luminous than it was when it first ignited. This gradual brightening is expected to continue, and in about 1 billion years, the Sun will be bright enough that the additional heat will likely push Earth's surface beyond the threshold for maintaining liquid water, triggering a runaway greenhouse effect similar to what we believe happened on Venus. Earth's habitability clock is not measured in billions of years. It is measured in hundreds of millions of years. Even by that far future measure, this bright window of planetary habitability we currently enjoy is already substantially used up. Around 5 billion years from now, the Sun will exhaust its hydrogen fuel and expand into a red giant. As it swells, Mercury and Venus will certainly be consumed. Earth may or may not survive the swelling, depending on orbital dynamics and the rate of the Sun's mass loss. But even if Earth's orbit expands enough to escape engulfment, the surface will be scorched to temperatures far beyond any chemistry's ability to sustain organization. Whatever remains of Earth at that point will be a bare, molten, radiation-blasted rock orbiting the swollen remnant of our parent star. The Sun's death will leave behind a white dwarf, a crystallizing ball of hot carbon and oxygen roughly the size of Earth. The outer layers of the Sun will form a planetary nebula, illuminated briefly by the white dwarf's ultraviolet radiation before dissipating over tens of thousands of years into the interstellar medium. That material will eventually become part of the next generation of stars if any more generations form. The Sun's atoms will return to the galaxy, and some fraction of them may, billions of years later, find themselves in new suns, new planets, perhaps new forms of life. Meanwhile, out in the broader galaxy, the decline in star formation continues. The Milky Way is already forming far fewer stars per year than it did in its youth. As the galaxy's gas reserves are consumed and as dark energy increasingly isolates our local group from cosmological sources of fresh gas, the rate of star formation will continue to decline. New stars will still form for many billions of years. Small, dim red dwarfs mostly, burning slow and steady, but the character of the galaxy changes. The brilliant blue-white massive stars that currently light up our spiral arms are not being replaced at anything like the rate they die. The galaxy is getting older, redder, quieter. The Andromeda collision, expected in roughly 4 to 5 billion years, will temporarily reverse this trend. When two large galaxies merge, the compressed gas between them triggers massive starbursts, brief intense periods of star formation. The merger of the Milky Way and Andromeda will likely produce a spectacular burst of new star formation, lighting up the merged galaxy with thousands of newly born stars. But this is a last gasp, a final flourish before the long decline. After the starburst fades, the merged Milkomeda galaxy will settle into the life of a typical elliptical galaxy, a slowly rotating ball of old red stars with very little ongoing star formation, gradually aging toward the degenerate era. About 150 billion years from now, dark energy will have pushed essentially all galaxies beyond our cosmological horizon. The Milkomeda galaxy and its remaining local group companions will be the only galaxies any observer in this region of the universe can see. The sky will appear to contain only a handful of galaxies, the local remnants, surrounded by pure darkness. Any astronomers alive at that point who had not inherited records from earlier civilizations would have no way of knowing that the universe had ever contained 2 trillion galaxies beyond their horizon. They would live in what appeared from their perspective to be an almost empty cosmos, having no access to the data that would reveal the universe's true history and scale. This thought has a certain chilling quality. We are privileged to live now, early in the stelliferous era, when the universe is packed with light, and the evidence of its history is visible in every direction we point a telescope. The expansion of space is our friend. In a way, it has separated the early universe from us in time enough to become a record. We can look out and see galaxies as they were when they were young. We can see the cosmic microwave background from 380,000 years after the Big Bang. We can piece together the history of the universe precisely because light from its past is still reaching us. That window is already closing, and it will eventually close entirely. Here's a thought that should hit you with genuine force. Of all the times that could ever have been conscious and aware and curious, we are alive in perhaps the most information-rich, evidence-rich, cosmologically interesting moment in the universe's entire history. Earlier we mentioned that the star formation rate peaked about 10 to 11 billion years ago, during cosmic noon, and has been declining by roughly 97% since then. We are not at the peak. We're well past it. But we are still in the era of abundant stars and galaxies and the rich chemistry they enable. The evidence of the universe's past is still all around us, in the light arriving from distant galaxies, in the composition of the cosmic microwave background, in the abundances of elements that record the history of nuclear synthesis. We are alive at a moment when the universe is old enough to have produced rocky planets and complex chemistry and biology, but not yet so old that the stars are going out and the data is being permanently erased, and we have, against extraordinary odds, developed the intelligence and the tools to actually read that data. Within the span of a single human lifetime, roughly the last 100 years, we have discovered that the universe is vastly larger than anyone previously imagined, that it is expanding, that its expansion is accelerating, that it began in a hot, dense state 13.8 billion years ago, that it contains 2 trillion galaxies, and that it will eventually undergo a slow, cold thermodynamic death after a span of time so vast it makes our entire history look like an afterthought. We have deduced the existence and properties of dark matter and dark energy, phenomena that together make up 95% of the universe's total energy budget, from the behavior of light and galaxies. We have detected gravitational waves from colliding black holes, confirming a prediction of general relativity made more than 100 years earlier. We have taken images of black holes using a telescope the size of Earth. We are, by any reasonable measure, living in the golden age of cosmology, the golden age of scientific exploration of the universe, a period when the questions are hard but the tools are good and the data is still available. Now let's think about that timescale in the framework we've built. The observable universe is 13.8 billion years old. The stelliferous era will continue for another 100 trillion years or so, assuming constant dark energy. In the context of the stelliferous era's full 100 trillion year span, we are at about 0.014%. But in the context of the full timeline of everything, including the degenerate era, the black hole era, and the dark era, we are at a moment so early that describing our position as near the beginning dramatically understates the case. If you mapped the entire expected duration of the universe onto a single year, from the Big Bang to the heat death, we would currently be in the first few milliseconds of January 1st. But here's the twist, and it's a twist worth really thinking about. Even though we are cosmologically early, we are not productively early. The universe's productive period, the stelliferous era, the time when stars burn and energy flows and chemistry is possible and life can exist, is not the whole universe. It is a thin, brilliant sliver. Most of the universe's timeline is dark and cold and dead. If you randomly selected a moment from the universe's total timeline and asked whether a conscious observer could exist at that moment, the answer would be overwhelmingly no. Because the vast majority of cosmic time is the dark era, when nothing capable of having experiences exists. We exist in one of the narrow windows when it's possible to exist at all, and within that window we exist at a time of particular richness, when the evidence is still fresh, when the lights are still on, when the story of the universe is still actively being written, rather than simply persisted as a frozen record in a dark and empty void. This is what it means to say we are living in the last seconds of the universe, not that the end is imminent, but that on any honest accounting of what the universe's total history looks like, the current era, the era of stars, of light, of biology, of consciousness, of curious beings pointing instruments at the sky and asking what's out there, is almost vanishingly brief. We are the brief, bright, improbable exception to a universe that is mostly dark and mostly cold and mostly finished. We are here in the flash. There is a philosophical choice you can make when confronted with the information in this video. You can find it crushing. You can look at the timescales involved, 100 trillion years until the last star, 10 to the 100 years until the last black hole evaporates, forever after that of silence, and feel the weight of it as a kind of cosmic futility. What does anything matter if the universe ends in maximum entropy? What is the point of a civilization, of a love, of a discovery, of a moment of beauty, if the universe is patient enough to erase every trace of it? This is not a stupid response to the information. It is a genuinely reasonable emotional reaction, and it has a long tradition in human philosophical thought. The ancient Epicureans thought about the death of the universe in their own way, and concluded that it underscored the importance of living fully in the present, of finding genuine pleasure and meaningful connection now, rather than deferring meaning to some infinite future. The Stoics thought about cosmic time and concluded it was a reason for equanimity. If even the stars are temporary, perhaps the ordinary frustrations of a human life deserve to be held a little more lightly. But there is another way to read the same information, one that we think is equally valid and perhaps more accurate. Consider what it means that we exist at all. The stelliferous era, brief as it is in cosmic terms, is the only period in the entire history of the universe when the conditions for complex chemistry and biological organization and conscious experience exist. Before the stelliferous era, the universe was too hot and too dense, and too different from what we know. After it, the universe will be too cold, too empty, too devoid of energy gradients for anything like life to persist. We are not just alive, we are alive in the one window when it is possible to be alive, and not just alive in the abstract biochemical sense, but alive in the sense of being able to stand back and understand what you are standing back from, to know that stars exist, to know how long they live, to know what comes after them, to hold in your mind the full sweep of 10 to the 100 years and feel the strangeness of it. That capacity, the capacity for cosmological understanding, for grasping the structure of time on scales billions of times larger than any individual life, is one of the most improbable and extraordinary things in the known universe. There is no thermodynamic reason for it to exist. There is no obvious necessity that the matter in the universe should arrange itself into patterns that generate self-awareness, curiosity, and understanding. And yet, here we are, in the thin, bright window, asking the questions. There is also something worth noting about the temporariness of our era specifically, the era of stars and its relationship to life and meaning. A universe that lasted forever in the stelliferous state, one where stars burned eternally, where the cosmic landscape never changed, where energy was always available everywhere, might not produce the urgency that drives both biological evolution and intellectual curiosity. The temporariness of everything, including stars and galaxies, and the energy gradients that life depends on, is not incidental to the drama. It may be essential to it. The second law of thermodynamics, the rule that entropy always increases, is the rule that creates time's direction. It is why there is a before and an after. It is why things happen rather than just are. Without the slow motion toward heat death, time would have no arrow, nothing would change. In a deep sense, the death of the universe is what makes the universe alive. The poet Rainer Maria Rilke once wrote, in a different context but the resonance is there, that beauty is nothing but the beginning of terror. The full view of the universe's timeline is exactly that. Beautiful and terrifying in equal measure, a vast ordered narrative that begins in fire and ends in silence, with a thin bright band in the middle where extraordinary complexity briefly flourishes, looks at itself and asks what it means. We are in that thin bright band. We are the universe's attempt to understand itself, happening in the only window when such understanding is possible. And when you internalize that, really internalize it, not just as an abstract fact, but as a lived felt truth, the experience of being alive changes texture, not in a paralyzing way, not in a way that makes the ordinary details of life feel meaningless, in a way that makes them feel almost unbearably precious. The coffee you had this morning, the light through your window, the face of someone you love, the night sky on a clear evening with its thousands of visible stars, each one burning through its own stelliferous lifespan, contributing its light to the brief cosmological moment in which you happen to exist. All of it is happening inside a window that is, by the universe's own standards, impossibly narrow. All of it is the stelliferous era in its last 13.8 billion year chapter. All of it is the last seconds of the universe. Let's lay it all out, from beginning to end, a timeline of everything, 0 years, the Big Bang. The universe begins as an unimaginably hot, dense point of energy. Space-time, matter, and the fundamental forces of physics emerge from conditions we cannot fully describe with current physics. In the first fraction of a second, the universe undergoes inflation, an extraordinary period of exponential expansion that stretches it from subatomic scales to macroscopic ones in less time than it takes light to cross an atomic nucleus. The universe is a homogeneous sea of quarks, leptons, and radiation. After a few minutes, the first atomic nuclei form: hydrogen, helium, and tiny amounts of lithium and beryllium. The universe is still far too hot and dense for atoms to exist. The electrons remain free, the plasma opaque to light. 380,000 years. Recombination. The universe has cooled enough for electrons to bind to nuclei. Atoms form for the first time. The universe becomes transparent, and the light released at this moment travels freely through space as what we now detect as the cosmic microwave background radiation. Around 400 million years, the first stars ignite. Vast, brilliant, short-lived population 3 stars begin fusing hydrogen in the densest gas clouds. The universe is rionized by their ultraviolet light. The first heavy elements are forged and scattered by their supernova. 1 billion years, the first galaxies are well established. The cosmic web of filaments, sheets, and voids that defines the large-scale structure of the universe is becoming clear. 3 to 4 billion years after the Big Bang, cosmic noon. The rate of star formation across the universe peaks. Galaxies are bursting with newborn stars. This is the brightest era the universe has ever been or will ever be. 4.6 billion years after the Big Bang, our sun forms from a cloud of gas and dust enriched by multiple previous generations of stellar evolution. 4 to 5 billion years from now, Andromeda and the Milky Way begin their collision over a period of several billion years. The merged Milkomeda galaxy takes shape as a large elliptical galaxy. About 5.4 billion years from now, the Sun expands into a red giant, transforms the inner solar system, and eventually collapses into a white dwarf. 100 billion years from now, most galaxies beyond the local group have receded beyond the cosmological event horizon. From our galaxy's perspective, the universe appears empty except for our immediate neighborhood. 100 trillion years from now, the last red dwarf stars exhaust their hydrogen fuel and fade to black. The stelliferous era ends. No more stars burn anywhere in the universe. The age of light is over. From 100 trillion to roughly 10 to the 37 years, the degenerate era. White dwarfs, black dwarfs, neutron stars and brown dwarfs cool toward absolute zero. Galactic dynamics scatter some stellar remnants into intergalactic space, while others spiral into central black holes. If proton decay occurs, all normal matter gradually dissolves into radiation and leptons. From roughly 10 to the 40 years to 10 to the 100 years, the black hole era. Only black holes remain, as organized structures. Supermassive black holes, the last organized objects in the universe, slowly evaporate through Hawking radiation, releasing bursts of energy as they shrink toward nothing. The last black hole evaporates sometime around 10 to the 100 years, one googol of years after the Big Bang. After 10 to the 100 years, the dark era. The universe is a vast, cold, nearly empty space filled only with low-energy photons, electrons, positrons and neutrinos spread so thinly across expanding space that meaningful interactions between them are essentially impossible. The universe approaches maximum entropy. Heat death. The big freeze. The lights are all out. The story is finished. And there it is, the entire arc. From a point of infinite density to a state of infinite emptiness. From a universe so hot and energetic that the word physics barely applies, to a universe so cold and still that the word time barely applies. From the Big Bang to the long, quiet, eternal equilibrium of the Dark Era. We are here at 13.8 billion years. We are in the stelliferous era. We are in the brief, luminous, improbable chapter, where stars burn and planets form and life emerges and looks up and asks what it all means. We are in the last seconds of the only era in which these questions can be asked. We want to be honest with you, the way good science communication demands honesty. There are crucial uncertainties in this timeline, and intellectual honesty requires acknowledging them. The biggest uncertainty is dark energy. We do not know what it is. We have measured its effects with extraordinary precision. The accelerating expansion of the universe is one of the most solidly confirmed discoveries in all of modern astronomy. But we do not have a fundamental physical theory that explains why the vacuum of space should contain a constant energy density, or whether that density will remain truly constant in the future. The fate of the universe hinges on this question. If dark energy truly is a cosmological constant, the universe ends in heat death. If it's a field with dynamics that grow stronger over time, we might get a big rip. If it somehow decays, we could get a big crunch or a vacuum decay event that changes the laws of physics entirely. Current measurements strongly favour the cosmological constant interpretation, but the error bars are not zero. Proton decay is another crucial open question. As we discussed, if protons are unstable, then all baryonic matter eventually dissolves. If protons are stable, the degenerate era stretches out much further, with white dwarfs and other stellar remnants persisting until other processes destroy them. Experiments searching for proton decay have so far found nothing, but the non-detection only constrains the half-life. It cannot prove that protons are truly stable. The information paradox surrounding black holes and Hawking radiation is also unresolved. When a black hole evaporates, what happens to the information about everything that fell into it? In quantum mechanics, information cannot be destroyed. It is always conserved. But in Hawking's original formulation, the radiation emitted by an evaporating black hole is thermal, random, and contains no information about what fell in. This is a contradiction between general relativity and quantum mechanics that has not been resolved. The resolution, when it comes, may require a new theory of quantum gravity, and that new theory could change our understanding of what happens in the black hole era and beyond. Loop quantum gravity, string theory, and causal set theory all offer different frameworks for combining quantum mechanics and general relativity, and they make different predictions about the universe at extreme scales, including the deep future. Some models of loop quantum cosmology suggest that what we call the Big Bang was actually a big bounce from a previous collapsing universe, implying a cyclic cosmology in which universes succeed each other in an endless series of expansions and contractions. Evidence for or against these exotic scenarios is currently extremely limited. What we know for certain, the universe is expanding. The expansion is accelerating. Stars have finite lifespans. Stellar death is inevitable. The thermodynamic arrow of time points toward increasing entropy. These facts are robust, well confirmed, and sufficient to establish the broad outlines of the universe's fate. The details, especially in the very deep future, are still subject to revision as our theoretical and observational tools improve. And there is something wonderful about that. The universe's ultimate fate is not yet fully written in our understanding. There is still discovery ahead. The questions raised by trying to understand the end of everything lead directly to the most important open problems in fundamental physics. Understanding heat death requires understanding dark energy. Understanding the degenerate era requires understanding proton decay. Understanding the black hole era requires solving the information paradox. The end of the universe, examined carefully, opens onto the most profound frontiers of physical knowledge. We've travelled a long way tonight, from the current moment through cosmic noon and the sun's death and the Milky Way's collision with Andromeda, through the extinction of the last red dwarf and the dissolution of matter in the degenerate era, through the slow evaporation of the last black holes in the darkness of the black hole era, and finally into the absolute quiet of the dark era, where entropy has claimed everything and time has lost its meaning. We have looked at the full map of time from where we are now to the furthest reaches of what physics can predict. So what do we do with all of this? First, we can appreciate it as an extraordinary scientific achievement. The fact that human beings, living on a rocky planet orbiting an ordinary star in an unremarkable galaxy, with brains that evolved primarily to solve immediate physical and social challenges, have nonetheless managed to deduce the large-scale structure and trajectory of the entire universe across 100 Google years of time. That is one of the most astonishing things that has ever happened. Science at its best is exactly this: the application of reason, mathematics, and careful observation to questions that dwarf the questioner by every conceivable measure. We cannot travel to the end of time, but we can describe it, we can map it, we can hold it in our minds. Second, we can use this perspective to recalibrate what matters. When the universe's full timeline is visible, certain things that loom large in ordinary life lose their grip on attention. The news cycle, petty conflicts, the social anxieties and status competitions that monopolize so much human energy. These things are not meaningless. They matter to the people involved, and we're not dismissing them. But they sit in a different relationship to time when you've just spent time thinking about heat death. The brevity of everything, the irreplaceable specialness of being alive and conscious in the stelliferous era, has a way of clarifying what actually deserves your attention. Third, and perhaps most importantly, we can take seriously the extraordinary privilege and responsibility that comes with being the kind of beings we are. We are, as best we can tell, among the most cognitively complex things in the observable universe. We are capable of understanding the universe on scales vastly beyond our immediate experience. We are the only known objects in existence capable of asking what the universe means. That is not a small thing. It is an astronomically, literally astronomically, rare and precious thing. If consciousness and understanding and the capacity for scientific inquiry are as rare and temporary as the universe's timeline suggests, then these things deserve to be protected, cultivated, and taken seriously. Not because the universe cares whether we understand it. The universe does not have preferences, but because understanding is one of the finest expressions of the stelliferous era's possibilities, and we are the universe's current best attempt at it. We talked about red dwarfs as the final stars of the universe, but to truly understand what the stelliferous era looks like in its closing chapters, we need to understand the full ecology of stellar life, as it exists right now, and how that ecology is changing. The universe is currently home to an estimated 2 trillion galaxies, and those galaxies together contain somewhere in the range of 200 to 400 billion trillion stars. Written out, that's approximately 2 times 10 to the 23 stars, and roughly the same as the number of molecules in a few grams of water. Each of those stars is a nuclear furnace, powered by the same process that makes hydrogen bombs function, converting hydrogen to helium through a cascade of nuclear reactions that releases energy in the form of light and heat. Stars range from barely there red dwarfs hovering just above the minimum mass needed to sustain fusion, at about 8% of the Sun's mass, all the way up to absolute monsters like the Pistol Star and R13601, which clock in at well over 100 solar masses and burn with a luminosity so intense that if you placed one where the Sun is, the Earth would not merely be uninhabitable, it would not exist, because the sheer radiation pressure would strip the atmosphere and eventually the surface itself. The lives of stars are dictated almost entirely by one parameter, mass, and the relationship between mass and lifespan is brutally counterintuitive. You might expect that a heavier star with more fuel would last longer, but the opposite is true, and the reason is that massive stars burn through their hydrogen at a ferocious rate. A star of 20 solar masses has roughly 20 times as much fuel as the Sun, but it is burning it at a rate millions of times faster, which means it lives only a tiny fraction as long. While the Sun has a main sequence lifespan of about 10 billion years, a star of 20 solar masses lives for only about 8 to 10 million years. A star of 100 solar masses lives for perhaps 3 million years, barely an eye blink in geological time, let alone cosmic time. These massive, luminous blue-white stars die young and violently, ending in supernovae that seed the galaxy with heavy elements. The Sun, by contrast, is a respectable middle-aged yellow dwarf. It has been fusing hydrogen in its core for about 4.6 billion years and will continue for roughly another 5 billion. It is currently at its midpoint, a comforting idea if you're trying to give the situation some perspective. Though, as we noted, the Sun's gradual brightening means that the window for life on Earth is already on its late side. The habitable window for complex life on our planet is probably not 5 billion years more but closer to 1 billion, because the increasing solar luminosity will eventually trigger a runaway greenhouse effect, long before the Sun reaches the red giant stage. Below the Sun in mass, you have a whole spectrum of smaller, cooler stars. Orange dwarfs and yellow dwarfs with masses around 60 to 90% of the Sun live for 15 to 20 billion years. These are stars that, if they formed early in the universe's history, are still burning today and will continue to do so for another 5 to 10 billion years. Several stars in the Sun's neighbourhood fall into this category: Tau Ceti, Epsilon Eridani, Alpha Centauri b. These are the stars that astronomers searching for long-term habitable worlds find attractive precisely because of their longevity. Then come the red dwarfs, which we've already discussed in some detail, but their extraordinary lifespans deserve further unpacking because the numbers are genuinely hard to believe. Proxima Centauri, the nearest known star to our Sun at 4.24 light-years away, is a red dwarf with a mass of about 12.3% of the Sun's mass. Its estimated main sequence lifespan is approximately 4 trillion years. That is 4 trillion years. The universe has existed for 13.8 billion years. Proxima Centauri is so young, in relative terms, that it has used up only about 0.35% of its total hydrogen supply. It is a baby. It will be burning long after our Sun is a cooling white dwarf, long after the Milky Way and Andromeda have merged, and the resulting Milkomeda galaxy has settled into an old, red elliptical, with no ongoing star formation, long after most of the current generation of stars in the universe have died. The smallest red dwarfs, those teetering right at the hydrogen-burning limit, around 8% of the Sun's mass, have estimated lifespans exceeding 10 trillion years. The universe is not even 1.4% as old as the time these stars will last. Every single red dwarf that has ever formed in the history of the universe, without exception, is still in its prime. Not one has aged out of the main sequence yet. The universe is simply too young for even the oldest, smallest red dwarfs to have exhausted their fuel. Below the red dwarfs are objects that form like stars but never quite ignite. Brown dwarfs. These are the failed stars, the objects that formed from collapsing gas clouds but never accumulated enough mass to sustain hydrogen fusion in their cores. Instead, they radiate slowly from the heat of their gravitational contraction, cooling gradually from temperatures that might reach a few thousand Kelvin down toward room temperature, and eventually approaching the temperature of the space around them. Brown dwarfs are extraordinarily common. Estimates suggest they might be as numerous as true stars, or even more common. They will persist through the degenerate era as cold, dark objects, gravitational but inert, until either proton decay dissolves them, or chance gravitational encounters scatter them into the void. Understanding this ecology helps us understand the texture of the universe's future. The early stelliferous era was dominated by massive, brilliant, short-lived stars that died young and spectacularly. The middle stelliferous era, where we are now, is dominated by medium-mass stars like the Sun, which burn steadily for billions of years. The late stelliferous era will be dominated almost entirely by red dwarfs, burning dimly but persistently over trillions of years, with brown dwarfs drifting coldly through the spaces between them. The universe's character changes dramatically across this span. The brilliant, colourful, chemically complex universe we inhabit is an early-era feature. The late-era universe is quieter, redder, dimmer, and far more patient. One of the questions that cosmologists and astrobiologists find genuinely fascinating is whether life, even life very different from anything on Earth, could persist or arise in the late stelliferous era, billions of years after our Sun has died. The red dwarf stars that dominate the late stelliferous era present a complex picture for habitability. On one hand, they are incredibly long-lived, giving any life that forms around them an enormous amount of time to evolve and develop. A civilization that arose on a planet orbiting a red dwarf 5 billion years from now, when our Sun is already a cooling white dwarf, could potentially persist and develop for trillions of years without their Sun dying. In principle, civilizations could arise and go extinct and arise again multiple times on such planets, with the stellar lifetime providing essentially unlimited time. But red dwarfs also present serious challenges for life. They are dim, which means they're habitable zones. The distances at which a planet's temperature allows liquid water are very close to the star. Planets in that zone are subject to tidal locking, where one side of the planet permanently faces the star and the other faces away. The day side can be scorching, the night side freezing, with extreme temperature gradients that create violent atmospheric circulation. Many red dwarfs also produce powerful flares, sudden bursts of ultraviolet and X-ray radiation, that, for nearby planets without thick protective atmospheres, could be sterilizing events. The Proxima Centauri system, which has a potentially habitable rocky planet called Proxima b in the right orbital zone, is subject to regular violent flares that would pose serious challenges for any complex life on the surface. None of this rules out life around red dwarfs. Life is remarkably adaptable, and the specific challenges of red dwarf systems might be navigated through underground habitats, deep oceans shielded from radiation, atmospheric chemistry that blocks harmful radiation, or biological adaptations that tolerate flares. Some astrobiologists argue that life around red dwarfs is not just possible but probable, given how numerically dominant red dwarfs are and how much time they provide. A Harvard astronomer, Avi Loeb, and his colleagues published research in 2016 arguing that, from a purely statistical standpoint, the probability of life in the universe increases over time, because the long-lived red dwarfs that dominate the future are actually better hosts for the slow evolutionary processes that produce complex life than the shorter-lived stars that dominated the early universe. By this argument, we may be early to the party. The vast majority of intelligent life in the universe may not exist yet. It may arise billions or trillions of years from now, around quiet red stars in a much dimmer, much older universe. That is a genuinely strange and beautiful thought. It suggests that the universe, from the perspective of its biological potential, is in some respects still in its infancy. The stelliferous era is not just ending. It is still in the part of its arc where the most biologically interesting developments are ahead of us, not behind. But even accepting the most optimistic scenarios for life around red dwarfs, the end of the stelliferous era eventually forecloses all of this. When the last red dwarf goes dark, there is no more free energy in stellar form, no more nuclear fire. The only remaining energy sources are the slow cooling of stellar remnants, and eventually hawking radiation from black holes. Whether life can theoretically exploit these energy sources is a question physicists and speculative thinkers have entertained. Freeman Dyson, the brilliant physicist and mathematician, argued in the 1970s that life might be able to persist indefinitely in a universe still cooling from the stellar era by slowing its metabolism and hibernating in the gaps between low-energy interactions. But this is deeply speculative, and the accelerating expansion of the universe likely renders it impossible in practice by separating everything from everything else. The degenerate era and beyond appear to be genuinely beyond biology, not just beyond our biology, but beyond any organization complex enough to deserve the name. We've talked about heat death as the universe's fate, but we haven't dug deeply enough into what entropy actually is and why its relentless increase leads inevitably to that outcome. This matters not just for understanding the physics, but for understanding why the universe's story has the shape it does. Entropy is one of the most misunderstood concepts in all of science. In popular usage, it's often described simply as disorder or randomness, and while that captures something, it misses the depth of what entropy actually measures. Formally, entropy is a measure of the number of microscopic configurations, arrangements of individual particles that correspond to a given macroscopic state. A glass of hot coffee has lower entropy than the same glass after it has cooled to room temperature, not primarily because the cooled coffee is more random in any intuitive sense, but because the uniform temperature state corresponds to a vastly larger number of possible arrangements of the individual water and caffeine and milk molecules than the non-uniform state. High entropy is simply more common, not in a normative sense but in a purely mathematical one. The second law of thermodynamics states that in any isolated system, entropy will never decrease over time, and in practice will almost always increase. The reason for this is essentially statistical. There are overwhelmingly more ways for a system to be in a high entropy state than a low entropy state. So if you start a system in a low entropy state and then let it evolve randomly, it will almost certainly move toward higher entropy, just because high entropy states are more probable. The early universe was in a state of extraordinarily low entropy. This is counterintuitive. The early universe was extremely hot and dense, which sounds like the opposite of ordered. But thermodynamic entropy is not just about temperature. It includes gravitational entropy. A perfectly smooth, uniform distribution of matter in a gravitational universe is actually a low entropy state, because gravity allows matter to clump together, and clumped matter, concentrated into stars and galaxies and black holes, represents a higher entropy configuration. The gravitational clumping of matter, paradoxically, is an entropy-increasing process. When gas clouds collapse into stars, entropy increases. When stars explode in supernovae and scatter their material through space, entropy increases. When stellar remnants cluster around galactic centers and eventually fall into black holes, entropy increases. Black holes, in fact, represent one of the highest entropy configurations of matter. The Bekenstein-Hawking entropy formula, developed by Jacob Bekenstein and Stephen Hawking in the early 1970s, tells us that the entropy of a black hole is proportional to its event horizon's surface area. A supermassive black hole has truly astronomical entropy, far greater than any star or planet or collection of ordinary matter of the same total mass. When things fall into black holes, entropy increases. When black holes themselves eventually evaporate through Hawking radiation, releasing thermal radiation, entropy increases again. Heat death, the big freeze. The dark era is the state of maximum entropy. It is the state in which entropy cannot increase further, because there are no more energy gradients left to exploit, no more concentrations of energy that can do work on their surroundings. In that state, the universe has used up all of its thermodynamic potential. Every process that could happen has happened. The universe is in equilibrium with itself, uniform at every scale. What is striking about this, and philosophically profound, though the physics itself is silent on the philosophy, is that the universe started in a state of extraordinarily low entropy, despite the fact that low entropy initial states are statistically rare. This is one of the deep mysteries of cosmology. Why did the universe begin so ordered? One answer comes from inflation theory, which postulates that the very early universe underwent a period of exponential expansion that smoothed out irregularities and set the initial conditions for everything that followed. But this simply pushes the question back a step. Why did inflation happen? What put the universe in the right initial state for inflation? Some physicists, including Roger Penrose, have argued that the extraordinarily low entropy of the universe's initial state is one of the deepest unexplained facts in all of physics. The universe could have begun in any of an enormous number of possible states, most of them high entropy and structureless. It began instead in a state of exquisitely fine-tuned low entropy, from which the entire subsequent history of stars, galaxies, life and mind followed inevitably. Why? We don't know. It may be something that physics can ultimately explain, or it may be a question that requires frameworks we don't yet have. What we can say is that the arrow of time, the reason that events happen in a sequence from past to future, the reason you can remember the past but not the future, the reason broken glasses don't spontaneously reassemble, is a consequence of entropy's increase. The direction of time is the direction of increasing entropy. In the dark era, when entropy is maximized and nothing can increase it further, there is no thermodynamic arrow of time. Nothing happens. No process can occur. And in that sense, the universe's death is not just a physical event, but a temporal one. Time's arrow dissolves, and with it the very scaffolding on which the narrative of the universe was built. The universe begins with a beginning. It ends with the end of endings themselves. We've described the most widely accepted cosmological scenario for the universe's future, the one supported by the best current measurements and most mainstream theoretical models. But science is a process of revision, and the honest view of the universe's fate must include the genuine uncertainties and alternative scenarios that physicists take seriously. The Big Rip is the first alternative worth examining in depth. As mentioned earlier, this scenario requires dark energy to have a different character than our current measurements suggest. Specifically, it requires the energy density of the vacuum to increase over time rather than remaining constant. The technical parameter that governs this is called the equation of state of dark energy, denoted by the letter W. If W is exactly -1, dark energy behaves as a cosmological constant, and the universe expands forever toward heat death. If W is slightly greater than -1, but still less than 0, the universe still expands forever, but the expansion rate eventually stabilizes at a finite value. If W is less than -1, what physicists call phantom dark energy, the energy density increases as the universe expands, leading to runaway acceleration. In the phantom dark energy scenario, the expansion rate eventually becomes so large that it overcomes not just gravity, which is already happening on cosmological scales, but also the electromagnetic forces that hold molecules together, the nuclear forces that hold atomic nuclei together, and ultimately the quantum field configurations that maintain the identity of elementary particles. The last few moments of the Big Rip scenario are truly violent. Galaxies shred, then solar systems, then planets, then individual objects, then molecules, then atoms, then the nuclei of atoms, then protons and neutrons themselves, before space-time itself tears apart. Current measurements constrain the equation of state of dark energy to be close to -1, with error bars that do not yet rule out phantom dark energy. As astronomical surveys like the Dark Energy Spectroscopic Instrument and future missions including the Nancy Grace Roman Space Telescope gather more data, we will narrow these constraints further. The Big Crunch is another scenario, though it is currently considered unlikely given the evidence. In this scenario, dark energy is not constant but instead fades over time, and gravity eventually wins the tug-of-war with expansion. The universe's expansion slows, halts, and reverses. Galaxies begin approaching each other. Eventually, the entire observable universe collapses in on itself, the reverse of the Big Bang, with temperatures and densities rising without limit as space contracts. In the final moments of the Big Crunch, the entire observable universe is compressed into a volume smaller than an atom. Some theorists, particularly those working on cyclic cosmology models, suggest that the Big Crunch could be followed by a Big Bounce, a new Big Bang, a new universe, a new cycle of expansion, complexity, and eventual collapse. In this view, our universe is not the first, and it will not be the last. The Big Crunch is not death, but transformation, the end of one cycle and the beginning of another. The Big Slurp, sometimes called vacuum decay, is perhaps the most immediately alarming scenario, even though on current estimates it is not likely to occur anytime soon. The Higgs field, which gives elementary particles their masses, is thought to exist in what may be a metastable state, not the absolute lowest energy configuration possible, but a local minimum in the energy landscape. If this is the case, quantum tunneling can, with some extremely low but non-zero probability, cause a small region of space to spontaneously transition to the true, lower energy vacuum state. When this happens, a bubble of true vacuum forms and expands outward at the speed of light. Inside the bubble, the physical constants are different, the masses of particles are different, the forces between them are different, and in all likelihood, atoms as we know them cannot form. The bubble expands at the speed of light, which means there is no warning. Nothing inside the expanding bubble survives. You would never know it was coming. The probability of vacuum decay in the current universe depends on the precise value of the Higgs field self-coupling constant, which in turn depends on the precise mass of the top quark. The measurements from the Large Hadron Collider have suggested that the universe may be in a metastable state, but the estimated decay time is orders of magnitude longer than the current age of the universe, probably longer than 10 to the 500 years or more, depending on the model. This is so long that it effectively means vacuum decay is not a cosmological concern on any timescale we need to plan around. But the theoretical possibility is real and unresolved, and it sits at the edge of our understanding of the Higgs mechanism. Finally, there is the possibility that our understanding of dark energy and gravity is fundamentally wrong in ways we don't yet appreciate. General relativity has been tested with extraordinary precision in the solar system, in binary pulsar systems, and in the detection of gravitational waves, and it has passed every test. But it is known to be incomplete. It breaks down at quantum scales, and the singularities it predicts inside black holes and at the Big Bang are generally understood as signs that it needs to be superseded by a more complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches to quantum gravity make predictions that differ from standard general relativity in the deep past and deep future of the universe. It's possible, not certain, but possible, that the universe's ultimate fate is different from what general relativity predicts, in ways that the correct theory of quantum gravity would reveal. This is not a reason for despair or skepticism about the science we've described tonight. The broad outlines of the timeline, the end of star formation, the death of the last stars, the eventual dissolution of matter and the evaporation of black holes, are robust predictions that do not depend on the fine details of quantum gravity. The qualitative story is well supported even if the quantitative details of the very deep future remain uncertain. But it is important to be honest about those uncertainties, because science's power comes precisely from its commitment to following the evidence wherever it leads, including into the admission of what we don't yet know. There is one more dimension of this topic that we haven't fully explored, and it is in some ways the most important of all: the psychological and philosophical relationship between human beings and the scales of time we've been discussing. Humans evolved to navigate time on scales of minutes, hours, days, and years. Our emotional lives are calibrated to seasons and lifetimes. Planning for 5 years in the future is considered forward thinking. Planning for 50 years requires serious effort and deliberate discipline. Planning for 500 years is essentially foreign to human political and institutional structures. Almost no organization that exists today expects to be around in 500 years in any recognizable form, and yet we've been talking tonight about timescales that make 500 years look the way a single second looks on the scale of a human lifetime. This mismatch between human temporal intuition and cosmological timescales is not a bug. It's a feature of how we evolved. Our ancestors who spent time contemplating timescales of billions of years instead of figuring out where to find food and how to avoid predators left fewer descendants. We are the children of people who were very good at focusing on immediate and near-term concerns. The capacity for genuinely grasping cosmological time is something we've had to build deliberately, through mathematics and science and the patient accumulation of evidence and reasoning over centuries, and yet the effort to build that capacity matters. Not because we'll ever need to act on the information that protons might decay in 10 to the 37 years, but because the act of genuinely trying to understand the universe on its own terms, rather than simply on the terms that our evolved psychology finds comfortable, is one of the most distinctly human and distinctly valuable things we do. It is the exercise of reason against the grain of instinct. It is the insistence on truth over comfort. Philosophers have long noted a paradox at the heart of the human condition. We are beings capable of imagining our own mortality, and therefore we live with the knowledge of our own finitude in a way that other animals apparently do not. Existentialists from Heidegger to Sartre to Camus spent considerable energy exploring what it means to be a being that knows it will die, and must nonetheless find a reason to get up in the morning. The knowledge of death, they argued, is both a source of anxiety and, when properly integrated, a source of authenticity and meaning. If you know you will die, you know that time is limited and that choices matter. The knowledge of cosmic mortality, the understanding not just that you personally will die, but that stars will die, that the universe itself will eventually reach a state in which nothing can happen anymore, is an extension of this existential confrontation. And it does the same work at a vastly larger scale. It puts the preciousness of the current moment in relief. It highlights the extraordinary improbability and value of what we have right now, in this brief, luminous, cosmologically unusual period when the universe is still full of stars and energy, and the kind of ordered complexity that makes experience possible. There is a concept in Japanese aesthetics called mono no aware, roughly translated as the pathos of things or the sadness of things, which refers to the bittersweet awareness of transience, the way beauty is deepened by the knowledge that it will not last. Cherry blossoms are not just beautiful, they are beautiful partly because they fall in a week. A sunset is not just colourful, it is moving partly because it ends. The stelliferous era is not just the age of stars, it is extraordinary partly because it will end, and because we are privileged to exist within it. Mono no aware, applied to cosmology, the universe is beautiful, and the universe is dying. We are here in the beautiful window between the Big Bang and the heat death. We are the cherry blossoms of cosmic time. That thought might make you sad. It might make you feel small. It might even make you feel that nothing matters, in the way that the phrase, "in the grand" scheme of things is sometimes deployed to dismiss what's happening in the present. But we want to suggest strongly that the opposite conclusion is the right one. If the universe is going to spend the overwhelming majority of its duration in a state of dark, cold, featureless equilibrium, then the current era, the era of fire and light and biology and mind, is not cheapened by its brevity. It is made more precious. The fact that this window is narrow is not a reason for nihilism. It is a reason for profound engagement with the reality of now. We are here. The stars are burning. The data is flowing. The questions are worth asking. That is not the last seconds of something ending. That is the first and last seconds of something extraordinary that will never come again in quite this form. Be here for it. We've been focused largely on the future, and where the universe is going. But to fully appreciate why our position in cosmic time is so extraordinary, it's worth spending more time understanding where we came from, specifically what the primordial era was like and what it took for the universe to reach the state we now call ordinary, the first second after the Big Bang, as a place where the laws of physics as we know them, tested in particle accelerators and satellite observations, are pushed to their very limits. In the first 10 to the power of -43 seconds, the Planck time, the smallest meaningful unit of time in current physics, conditions were so extreme that our best theories break down entirely. The energy density was so high, the temperature so inconceivably hot, that quantum gravitational effects dominated everything, and our current mathematics cannot reliably describe what was happening. This is the singularity, or near singularity, of the Big Bang, the place where our story begins, but where our tools for understanding it run out. What we can say with confidence begins at about 10 to the -36 seconds, when the universe is thought to have undergone inflation, the period of exponential expansion that blew the universe up from a subatomic scale to macroscopic scale in an extraordinary fraction of a second. The details of inflation are still being worked out, but the broad picture is supported by the patterns we observe in the cosmic microwave background. The slight temperature variations in the CMB, the tiny overdensities and underdensities that are the seeds of all future large-scale structure, match what inflationary models predict. Those slight wrinkles in the fabric of the early universe are the reason galaxies exist. If the early universe had been perfectly smooth, gravity would have had nothing to work with, and the universe would have remained a uniform soup of particles forever. The wrinkles created by quantum fluctuations during inflation, magnified to macroscopic scales by the expansion, gave gravity the toehold it needed to start building structure. By 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Kelvin. Protons and neutrons were forming and interacting. The ratio of protons to neutrons was shifting as the conditions changed. Between about 3 and 20 minutes after the Big Bang, a process called Big Bang nucleosynthesis occurred. The universe had cooled enough for protons and neutrons to bind together into atomic nuclei without immediately being torn apart by thermal collisions. During this brief window, approximately 1/4 of all the ordinary matter in the universe was converted from hydrogen into helium-4, with trace amounts of deuterium, helium-3, and lithium-7 also produced. After about 20 minutes, the universe had cooled and expanded enough that nuclear reactions stopped. The ratio of hydrogen to helium was locked in, roughly 3 parts hydrogen to 1 part helium by mass, and it has remained essentially that ratio in the bulk of the universe ever since, though subsequent stellar nuclear synthesis has added heavier elements over billions of years. For the next 380,000 years, the universe was a hot, opaque plasma, a fog of free electrons, protons, and helium nuclei, all interacting energetically with photons. Light could not travel freely. It was constantly scattered by the free electrons. Then, when the temperature dropped to about 3000 degrees Kelvin, the electrons and nuclei combined to form neutral atoms for the first time. This is the epoch of recombination, and it's the moment when the universe became transparent. The photons that had been trapped in the plasma were suddenly free to travel without scattering. They have been traveling ever since, for 13.8 billion years, cooling as the universe expanded, and we detect them today as the cosmic microwave background at a temperature of 2.725 Kelvin. After recombination came the cosmic dark ages, a period lasting several hundred million years during which the universe was filled with a cooling gas of hydrogen and helium, without any stars or other sources of light, growing darker as the residual heat from the Big Bang faded. The universe during the Dark Ages was genuinely dark. If you could have been there, you would have seen nothing, because the CMB radiation had already shifted into the infrared and microwave range, invisible to human eyes. It was, in some deep sense, the quietest and most featureless phase the universe has ever experienced, even more featureless perhaps than the dark era to come, because at least in the far future there will still be particles interacting with each other, even if only very slowly. During the Dark Ages, the universe was a quiet sea of gas, waiting. Then the first stars ignited, and the universe was never dark again, at least not during the stelliferous era. The ultraviolet light from those first massive stars began reionizing the surrounding gas, creating a wave of transformation that gradually cleared the cosmic fog. By about 1 billion years after the Big Bang, the universe had been fully reionized. The intergalactic medium, the gas between galaxies, had been converted back into a plasma, this time thin and hot rather than the dense opaque plasma of the early universe. The universe we can observe with our telescopes, the universe of galaxies and cosmic web and large-scale structure, was taking shape. This history is not just academic background. It is the context that makes the stelliferous era what it is. The chemical complexity that makes biology possible, the carbon and oxygen and nitrogen and iron and dozens of other elements, did not exist at the start of the stelliferous era. It had to be built, slowly and laboriously, generation by generation of stellar evolution. The first stars made the first heavy elements. Their supernovae scattered those elements into the interstellar medium. The second generation of stars formed from slightly enriched gas and made more complex chemistry. Each generation building on the last over billions of years until the chemistry was rich enough to form the organic molecules that are the precursors of life and eventually the complexity of living systems themselves. We are not just lucky to be alive during the stelliferous era. We are lucky to be alive late enough in the stelliferous era for the necessary chemical complexity to have accumulated. Early universe life, if it existed at all, would have had essentially no heavy elements to work with. Stars made from pure hydrogen and helium without any metals, as astronomers call all elements heavier than helium, have different properties and produce different environments than the Sun and its solar system. The fact that we have carbon-based biochemistry, that we have planets with iron cores and silicate mantles and oxygen atmospheres, means that our existence required not just the stelliferous era, but a specific relatively late phase of it. We are, in this sense, a product of the universe's own history accumulating. We are what happens when a universe that started in nearly featureless simplicity runs long enough and makes enough generations of stars to build the complexity needed for something like us, and we exist in the specific window where that complexity is possible, after enough stellar generations to make us but before the stellar era ends and the energy gradients that support complexity vanish. One of the strangest things about cosmology's long-term forecasts is that they require us to reason about time intervals so vast that our ordinary mathematical intuitions fail in ways that can lead us badly astray. So let's spend a moment thinking about how cosmologists actually handle these numbers and why the way you frame a comparison between time intervals can change the emotional and conceptual impact dramatically. Consider, the current age of the universe is 13.8 billion years. The last star is expected to burn out in about 100 trillion years. That sounds like the end is a long time away. 100 trillion years. But 100 trillion is only about 7,250 times larger than 13.8 billion. The ratio is comprehensible if not comfortable. The degenerate era, from 100 trillion to 10 to the 37 years, is far more extreme. The ratio of 10 to the 37 to 100 trillion, itself 10 to the 14, is 10 to the 23. That ratio is larger than the number of stars in the observable universe, and the black hole era extends from 10 to the 40 to 10 to the 100 years, a range that makes the degenerate era look brief by comparison. The dark era has no endpoint. One useful way to think about this is with the logarithmic scale that Adams and Laughlin use. If you plot cosmological time on a logarithmic axis, where each unit represents a power of 10, then equal distances on the axis represent equal factors of increase rather than equal absolute increments. On this scale, the stelliferous era spans from cosmological decade 6 to cosmological decade 14, a span of 8 units. The degenerate era spans from about decade 14 to about decade 37, a span of 23 units, nearly 3 times as long as the stelliferous era. The black hole era spans from about decade 40 to decade 100, a span of 60 units, roughly 7 times the length of the stelliferous era, and the dark era begins at decade 100 and has no known endpoint. Visualizing this as a simple horizontal timeline reveals the structure clearly. The stelliferous era, the age of everything we know and love, is a narrow band on the left side of a chart that extends almost infinitely to the right in dark and cold. We are a footnote in the universe's temporal accounting, a brief bright flash in an otherwise dark document. But here's the mathematical insight that makes this more interesting rather than more depressing. The Dark Era's infinite duration does not make it more significant in any experiential sense. Duration is not the same as information content or complexity or the capacity for anything to happen. An infinite period during which nothing happens does not accumulate meaning the way a finite period full of events does. If you measure the universe's story in events, in things that happen, changes that occur, structures that form and dissolve, information that is processed, then the Dark Era's infinity contributes almost nothing to the total. The universe's story is essentially all told by the time the last black hole evaporates. What comes after is a kind of eternal silence, not a continuing narrative. In information-theoretic terms, the universe's total complexity, the total amount of meaningful change and structure processing, is finite, even if its temporal duration is infinite. Almost all of that information content is concentrated in the stelliferous era and the early degenerate era, when structures are complex and energy gradients drive processes. We live in the information-dense part of the universe's history, and that, perhaps more than any other framing, is what makes the present moment truly extraordinary. Before we close completely, we want to sit with one more idea, the one that, if we're honest, is the whole point of everything we've covered tonight. Every civilization that has ever existed on Earth has existed during the stelliferous era. Every piece of music ever composed, every mathematical theorem ever proven, every war ever fought, every child ever born, every book ever written, every prayer ever offered, every moment of love or grief or wonder or discovery. All of it has happened inside this narrow band of cosmic time when the universe was bright enough and warm enough and chemically complex enough to support the kind of matter we are made of. We sometimes speak of the present moment as ordinary, as routine. We wake up, we go about our days, we sleep, we wake again. The sky is familiar. The sun rises reliably. The seasons cycle. It all feels like it has always been this way and always will be. But it hasn't always been this way. There was a primordial era when nothing we recognize existed, and it won't always be this way. There will be a degenerate era when no stars burn, a black hole era when no planets orbit anything, a dark era when the very concept of a sky has no referent. The ordinariness of now is itself extraordinary. The familiarity of it. The fact that you can walk outside and feel the sun on your face, which is to say the fact that there is a sun, which is to say the fact that the universe is in the exact right phase of its history for nuclear fire, to be burning in a yellow dwarf 93 million miles from where you are standing. The fact that there is an atmosphere to carry the warmth. The fact that there is a biosphere complex enough that you are alive to feel it. Right now, tonight, the sky outside contains roughly 5,000 stars visible to the naked eye from a dark site. Every one of those stars is a nuclear furnace, some burning for millions of years, some for billions, some of them with planets, some of those planets possibly with life. The Milky Way stretches overhead as a band of light that represents hundreds of billions of stars. Beyond our galaxy, 2 trillion more. The observable universe, 93 billion light-years across in commoving distance, containing everything that light has had time to reach us from since the Big Bang. All of it, right now, inside the stelliferous era. All of it still burning. The universe has been dark before, in the cosmic dark ages between the recombination and the first stars. It will be dark again, permanently and forever, when the last star dies. We are between those darknesses, in the light. In the one era when the light exists. There is a moment, if you've ever been somewhere truly far from city lights, and have had the chance to simply lie on the ground and look up at the Milky Way, when the scale of it becomes briefly real. Not just intellectually real, the way reading about billions of stars makes it real, but viscerally, bodily real. The sky above you is deep in a way that the daytime sky is not. The stars are not a flat backdrop. They are a volume, stretching away in all directions, and you're very small and very temporary in the middle of it. That moment, if you've had it, is the closest most of us get to genuinely feeling the size of the universe. What we want you to take from tonight is something like that moment, but extended. Not just the spatial vastness of the universe, but the temporal vastness. The fact that when you look at those stars, you're looking at objects that are burning in the last cosmologically brief instant of stellar time. That the darkness between those stars has already lasted far longer in the past than the stars themselves, and will last far, far longer in the future. that you and the stars and the planets and the entire stelliferous era together are a thin, bright band between two darknesses. That thinness does not make you less, it makes you more. It makes this moment, all moments, more. It makes the fact that anything exists, that the universe went to the trouble of producing complexity and consciousness and curiosity in this brief window between silences, feel like the most remarkable fact in all of physics. You are here, you are asking, you are looking up. In the universe's own long reckoning, that is everything. The stars are still burning. Look up tonight. They won't be burning forever, but tonight they are. And we'll see you next time for another journey into the cosmos that made us. See you later, guys.